He lives and works in Boise with Idaho Power. And this talk is so high tech that he's gonna have to quit recording stuff and you're gonna have to be sworn to secrecy or he's gonna kill you. No, but there is some stuff that's kind of proprietary and he'll talk about that. That'll be really interesting. So Derek went to school for atmospheric science in North Dakota, University of North Dakota, got done in 2003, and then started working on weather modification. Let him explain that a little bit more. But in that general field, which is something near and dear to all our hearts, in the western US and western Canada and India, all places too, which sounds interesting. And then he went to work for Idaho Power back in, here's that? 2008. Yep. So yeah, he's been working with them since then on Idaho Power. And for those of you that don't know, you can see the title slide, but they have a cloud seeding program that actually does have some kind of local implications, and we'll hear about that, and then I'm sure there'll be plenty of questions for you.
All right, thanks, Scott.
Thanks, Eric.
We'll try to get through a lot of data here in a hurry. Like you said, I'm Derek. Little overview of what I'm going to talk about today. We'll get into what is cloud seeding, then how is cloud seeding done, a little bit of what Idaho Power does with cloud seeding, some of our projects, so looking around the state, including right here in the Wood River Basin. Then we'll get into some of the benefits that we have, and then what he was talking about, or we'll turn the camera off, our snowy project. This just concluded. We had a bunch of researchers here from different universities. Until that's published, we can't really put the data out there for everybody to grab online, so we'll stop at that time, and then we'll get into some frequently asked questions there at the end, and then yeah, we'll go from there. So what is cloud seeding? Cloud seeding is basically using supercooled water in a cloud. There's water that doesn't freeze at 0 or at 32 degrees Fahrenheit. Water is actually really dumb. It doesn't freeze. It can actually exist all the way down to minus 40 degrees in a liquid state before it freezes. And how a cloud works, it needs something to go in there and teach that water how to freeze, and it starts to fall out. What we do is we get into there and we monkey with that a little bit, how nature actually works with producing that. I'll talk about that a little bit in a second. But there's 4 major types of cloud seeding. There's fog suppression. If you ever go to the Boise airport, in the wintertime, the fog depth might come in. They'll do some cloud seeding and clear right around the runway, and it will be able to clear the fog and planes can land. There's hail suppression. This is what I originally began working with cloud seeding with. This is taking the big thunderstorms and you try to reduce the amount of, or reduce the size of the hail or the amount of hail that happens within that thunderstorm. This helps protect crops. It helps protects vehicles and infrastructure and that stuff. There's also rain enhancement. This is a little, kind of almost a bystander to the hail suppression. You're able to increase the precipitation slightly when you reduce the hail. And also there's snowpack enhancement. That's what we're primarily doing here in Idaho and across the western United States. And how that works, like I was talking about the super cool liquid water, each one of those, that water it just exists in a natural state. And without something to teach it how to freeze, that water just kind of floats over the mountain and drops down the other side and continues on. If there's an ice crystal, a dust particle, something else that's there in nature that comes in contact with that super cool liquid water, it starts growing and snowflake really fast. You can kind of look at it the same when you're skiing and it's in cloud and you have that leading edge of your chairlift starts to produce all that ice right in front of it as it's going around the mountain. That is the same thing as what we're doing in nature, is putting those chairlifts out there. As it moves through that cloud, it's producing the ice on the front edge, so you start that ice process. Once that ice starts growing, it grows quite fast. It starts depleting the water that's around it. So originally you have your natural state of water that's in the atmosphere, and then you start to accumulate water and it starts growing that hexagonal snowflake, and that continues to grow. Once it gets to the size, it's kind of a dendrite here. You start branching out and you start getting these other crystals that form on the outside. They can break off and start a new snowflake and keep going that way. And this is basically how nature produces snowfall. It starts that process and then it expands out. What cloud seeding does is, instead of a dust particle, there's not enough dust particles in nature, we put silver iodide into the cloud, and that starts that process of growing a snowflake. And it actually works a little bit warmer than what natural occurring ice nuclei does, or the dust. Instead of dust usually works around about 5 degrees Fahrenheit. With the silver iodide, we can get it as warm as 23 degrees Fahrenheit when you start that process of growing a snowflake. And so you get more time within that cloud if you're able to start growing that snowflake a little bit more, or a little upstream in the mountain range. You got longer time to grow that snowflake to the size that it can actually fall out and get down to the ground as precipitation. How we get that silver iodide into the cloud, we use two mechanisms. One is our ground-based generators. These are basically, it's almost like a hibachi burner that's up on the top. It's a propane flame, and and within there we inject an acetone solution. Inside that acetone has a silver iodide that's suspended into it. This one's burning. You see that you don't see the smoke, but the exhaust or the smoke that comes out of it, that has a silver iodide particles in it. That gets transmitted into the cloud, and those disperse and start the growing of the snowflakes. The other mechanism is using an aircraft, and the aircraft has two mechanisms. One is a burn-in-place flare. These burn like a road flare. The pilot will ignite them, and it'll start burning from the back to the front, and the smoke from that has a silver iodide, and it starts emitting. These stay with the plane, so as the plane transitions through the cloud, it basically leaves a trail of smoke behind it with the silver iodide to start growing those snowflakes. The other mechanism is this cartridge underneath it. These are ejectable flares. They're the same thing as a cardboard tube. It kind of looks like a shotgun shell that it's in. And when you eject those, that tube falls out of the aircraft, and then it burns up as it falls down. It burns up in about the first 2,000 to 2,500 feet as it falls down, and this emits the silver iodide, and that goes on. So when I talk about the snowing, these are the two mechanisms that we'll be talking about dispersion when we look at some of the results. You'll be able to see the burn-in-place flares as they trail through, and then you'll see the individual ejectable flares as they fall out. So who does cloud seeding? In the Midwest states and actually through the Central Plains, all these green little dots, Texas, Kansas, North Dakota, Alberta, these are summertime stuff. So it's your hail suppression and your rain enhancement. Down in Texas, it's all rain enhancement. North Dakota is mainly hail suppression, but it has some rain enhancement components. Alberta is a cool one that was actually funded by insurance companies to protect the towns of Calgary and Red Deer from hailstorms that come through there. They have a potential for $1 billion worth of damage from that single hailstorm that moves through the city. And so if they're able to reduce that by 10% or even 20%, that's a huge benefit for the insurance companies. So that's why they fund stuff out there. Here in the western United States, all these blue places, those are the current wintertime snow enhancement projects that we have going on. Some of the oldest projects are in California. Here in Idaho, we're relatively new. Why Idaho Power gets into cloud seeding is we're a hydro-based utility. Roughly on average, half of our electricity that we produce comes from hydroelectricity. Our main three dams are the Hells Canyon Complex. That's further down on the Snake River. It's the end of our system. Roughly half our hydropower comes from those three facilities. And so what cloud seeding does is we're trying to create a little bit more water within the Snake River plain, and that can get into our reservoirs or our hydropower, and that produces our cheapest electricity, and that helps to keep the cost of electricity low here in Idaho. Little history of cloud seeding. Back in 1993, a shareholder came and said, hey, why doesn't Idaho Power cloud seed? And so we, from there we started a literature review, and it wasn't until 2003 when we got an actual project started, and this was in the Payette Basin. That's our longest run project. From there we started growing. 2008 we moved into the Upper Snake region with the High Country RC&D. They asked us if we wanted to partner with them. That's where we started working with there, and also through the camp process. We continue to expand in the Upper Snake into western Wyoming. And then in 2011, we started working with the National Center of Atmospheric Research, and we're trying to develop models to actually model cloud seeding, to see what the results are using a computer model that we have. In 2013, that's when we actually started cloud seeding in the Wood River Basin. The Big Wood Irrigation, our canal company, asked us if we're not flying our aircraft in the Payette, we'd fly in the Wood River Basin to try to create a little bit more precipitation here. From then we've continued to grow. Our current project, or actually let's jump ahead to more of our current project. In this past year, 2016, 2017, we're up to 55 ground-based generators across the state of Idaho. And we're now up to 3 aircraft. 1 aircraft is dedicated for the Boise and Wood Basins together that we have. And as we continue to grow, we'll continue to look for opportunities, whether it's more aircraft or more ground-based generators and where they go. A look at where cloud seeding happens. Here's a map of southern Idaho. This is the Idaho-Wyoming border. Idaho-Montana's here. The Payette Basin is up in this area. The Boise Basin, the Wood Basin, Sun Valley, we're right here for right now. Currently in the Boise and the Wood Basin, there's 13 ground-based generators. That's all these little plus marks, whether they're the orangish ones or the pink ones. Those are where we have our ground-based generators set up. These lines that we have going around here, these are preset flight tracks that we have. When the weather conditions are correct, let's look at this guy right here, which is our 8 Charlie track. When the winds are coming out of the west-southwest, we can fly the aircraft on there, and that will seed for downwind. And that's kind of how the aircraft works. We also, this past year, we have a couple of high-res precipitation gauges in the area. We also launch weather balloons or Ray-Winson units to try to figure out what the weather's happening. What our project will look like in the future, this map didn't actually change. We don't have any stuff plotted, but we looked at in the Boise and Wood Basin, there's probably potential for double the amount of ground-based generators that we have. And then we'd also like to add some more weather sites that we have to help monitor the weather and help to try to figure out what's going on with cloud seeding, what our benefits are. Now let's get into some of our benefit estimates, how we actually look at does cloud seeding work. Historically, the first way that we started doing it was a target control analysis. This is kind of an industry standard. It's the easiest way of doing stuff. Cloud seeding is a lot like global warming, like HP was talking about earlier. It's hard to actually prove statistical significance that it actually works or it's there. You can see it, you can see the results that all hint towards the benefit, but to actually see it has been very difficult to come to that level of confidence. Target control analysis is one of the ways that we start to say, hey, we think cloud seeding works using this. In the Payette Basin, this was our longest run cloud seeding basin, and we looked at years before cloud seeding happened. What we did is we plotted what happens with precipitation gauges that are outside the target area, and then look at precipitation that's inside the target area. This bottom line is the total amount of precip outside the area, outside the target area, and this is precipitation inside the target area. And you look at each year, this much fell outside, this much fell inside, and you make that point. And then you plot multiple years before cloud seeding happens, and you get basically a regression line of what or where you expect stuff to happen. If you cloud seeding and those dots are above the line, you can say, hey, that difference equates to the benefit from cloud seeding. If it's below the line, then you would have a negative effect. Since 2003, every year has been above that line. There's been a couple years that have been close, these years that happened, but every year was above. If you actually look at the average, this comes out to roughly about 14% increase that's happened within the Payette Basin that's since cloud seeding began. These numbers are not this year's numbers. This is all based on the April 1st SWE values. These are last year's numbers that we had. Just using the target control analysis, we came up to Payette Basin, had over 11% increase. Here in the Wood Basin, we had over a 5% increase, and we're not fully built out in that basin. We actually went back and we started looking at these years that came really close to the line. We set up a March 1st regression equation to look at that, because these years started to melt out really soon. They were warm years, and that actually jumped it up, and it was on par with what we expect to have in those years too. So a lot of this has to do with when melt happens and everything else, but it's pretty cool that every year has been above normal. Just naturally you'd think that some year would have to be below normal, even with cloud seeding, but we're still above normal. We can take that roughly 14% increase and actually run it through some of our hydrologic models that we have at Idaho Power to figure out what type of benefit does that include in the rivers. If you just look at the Payette Basin, we did kind of the same thing. We took 50-year record and we ran our hydrology models, and then we took that same 50-year record and put a 14% increase on it, and to determine what average 14% increase would have over the time period. And just in the Payette Basin, that equals to about, oops, wrong button, about 270,000 acre-feet of water, which is substantial. If we did the same thing looking at the Boise and the Wood Basins, and with a 10% increase in the Wood River Basin, you're looking at over 80,000 acre-feet of water, of additional water each year that comes from cloud seeding, or has the potential to come from cloud seeding. Some of the runoff benefits that we've estimated at build out, actually this got distorted. The Wood River Basin, as we continue to build, continue to add generators, we think we can get that number up closer to what the Payette has for an increase, and that's going to be closer to 120,000 acre-feet of water that's in the basin. The last thing I'd like to get into before our research is we started running a high-resolution atmospheric model looking at weather across the southern Idaho. We use this at the University of Arizona. Your normal weather models are, your spatial resolution are pretty extreme. They could be anywhere between 10 kilometers and 60 kilometers, depending on how old that is. With the University of Arizona, we run the WRF on top of those models, and that gets the resolution down to 1.8 kilometers or 1 mile. And with that grid spacing, we're able to get a higher temporal guess at what's actually falling on the ground. When we started running that model, we started building the snowpack across the basin, and we tried to determine, can we match the snowtail sites up with the model data just running through the year. We looked at gauges that were outside our target area. So the Van Wyck site that's upwind, so it's not affected by cloud seeding. And we plotted the model data, which is in the dashed line, next to what the snowtail site had for precipitation through the year. And it actually came up pretty well, tracing the snowpack through the season. We did multiple sites, and it was pretty similar across the board. Typically the model overestimates the amount of precipitation that falls, but it was in the neighborhood of what you would expect to see, about a 10% difference that we saw. Then we started plotting the snowtail sites within our target area, and we saw that the model data continuously underestimated the amount of snowfall that fell. And from this, because the WRF model doesn't know that cloud seeding is happening, and it continued to do this. So from here, we started working with NCAR to try to figure out, hey, can we actually model cloud seeding, model the benefit based off of these models?